Hi guys, sorry for the delay. I had a meeting that's took a little bit longer. Any question before we start? All right. So today we're gonna talk. Continue talking about the microarchitecture, and then we're gonna talk about data path and controller. Uh, so last time we talked about what is the microarchitecture, what is data path, what is controller, why we need them, and then we kind of like very quickly talk about some of the basics. We kind of show that the von Neumann model, the computer model that we have, is essentially a CPU and a memory. It has some inputs and outputs, and also let me change the color. All right, and inside the CPU is basically has two different units: the data path and the controller. We then talked about the life cycle of the instruction. We basically said that there are 5 different stages that the instruction has to go through in order to being executed. The first one was fetching the instruction from the instruction memory. Then we had to deal with the operand. We said that there are 3 different types of operand: the register file, the memory, and the immediates. Then we also talked about the actual operation, which could be some arithmetic, could be some dealing with the memory data and so on. And then we talked about the storage, that the data needs to be stored. And then finally, we need to update the PC, okay? And then we kind of started to talk about each of these units. So in this lecture, we're gonna go through the actual details of each of these steps. And then we said that the main challenge is that since every different instruction has a different, activity, some of them needs to load 2 different registers, some of them needs to just load 1 register, some of them needs to access the memory, some of them don't. We technically need this additional unit called the controller, which kind of orchestrates the behavior of each of these instructions. And then we kind of like finish at this point at how to build a controller, okay? And so the first thing that we want to talk about today is building a controller. And probably if you've you already know that for building states and something that has some different states in the program, you need something like a finite state machine, okay, or FSM. FSM is basically the mathematical model of the computation. Essentially, the system can be modeled as number of finite different states that at each point the program can be at one of these states. So for example, for our specific example, you can think about as all those 5 steps that I described, and each of them could be one of the steps or one of the states that we need to program our finite state machine for it, okay? And then FSM, probably as you know in your M16 course, FSM has different states and the condition that transition from one state to another state, okay? And then all the inputs and outputs from each state to another state. So usually like an FSM looks something like this, that you have, let's say, for example, 3 different states. You have conditions from moving from one state to another state. And then you have some conditions from, for example, staying at the same state over and over again, or from, for example, moving from one state to another state, okay? So these are usually the way that the FSM works. We're not gonna go through the how to design the FSM itself because it's something that you probably have seen before, but I will ask the TAs to go over some of the details of the FSM. Any questions so far? So for the FSM that we particularly interested is the actual controller in our processor. And you can think about this as a giant FSM with many different states because we have many different instructions. Each of them have many different states. and stops. Sorry, I forgot to start actually. Right. Okay. So each of them has many different, states and steps. So we need to actually take care of all of these different things. Okay. So basically, if you think about the life cycle of instruction that we just talked about, uh, all of these instructions start with this initial state, which is basically reading the instruction and decoding it. So everybody start from this main state here, which is the getting the instruction from the instruction memory. Then basically, depending on what instruction we have, now we have different branches basically out of this initial state. For example, if it's a load, if it's a store, if it's an add, etc., etc. Okay, so basically you can think about this that everybody start at this initial state, which is basically decoding the instruction, and now depending on what is the opcode, everybody goes into their own state. Okay. And then what happens after that is that depending on what the instruction is trying to do, we're gonna go through different states. For example, the load might need to go through the memory and then execute the instruction, update the PC, and so on and so forth. And at the end, all of them has to circle back to this initial state. Okay, so everybody has to go back to the decoding the instruction again, and basically that would be the part that we're gonna start the new instruction. Any questions so far? And then, as I said, once all of these, states for every different instruction has been, covered, then we go back to the initial state and repeat this process for the next instruction and next instruction and next instruction. And that's how we actually, execute all of these instructions in our processor. So to give you a little bit more perspective and go through the examples, from now on, we're gonna build this very simple processor, okay? So the processor that we're gonna build is basically just a handful of instructions. So we already covered most of the instructions, but for implementation, we're gonna just, focus on these 10 different instructions. The instructions that we're gonna cover is add, subtract, and, or, load word, store word, and branch equal. And then we're gonna also have like immediate instructions such as add I, and I, and or I. Okay, so these are the 10 instructions for now that we're gonna care about. We just picked these 10. We just picked pick this 10 in order to have some diversity, but we could have easily taken another sort of instruction. There you go. Yeah. Any other questions? All right. So now from now on, we're gonna focus on how to implement this in our processor. This is the more detail of the instruction that we're gonna have. These are all the R type instructions. These are all the I type instruction, load word and store word, and the branch equal. Okay. Probably things to note is the opcode, the func3, and the func7. So as you can see, all these R type instructions has exactly same opcode. The only thing that is different from them is func3, as you can see here. And even for add and subtract, even the func3 is the same. The only thing that is different is func7. So essentially, in order to understand that whether this is an add or a subtract instruction, we kind of need to go through 3 steps. We have to first check the opcode. And then we're going to see that, for example, the opcode is 0110011. So at this point, we know that the instruction could be one of these 4. Then we have to go and check this func. If the func is 00, then we know that it's either add or sub. Then we need to check this one, and then now we know that whether it's a sub or whether it's an add. But for the others, you can see that the opcode is actually different. So the add I, for example, opcode is different than the add instruction. But again, for all the immediate instructions, the opcode is exactly the same. But the opcode is different from, for example, load, or from the store, or from the branch. Question here? Yeah, this is bit 0, so it's to start from right. So we have this is basically the 32-bit instruction that we have. On the left one is funct 7. What's that? Funct 3, yes. Yeah, there's the you always can refer to that table that we gave to you if you have like doubt that what this is basically. The left is, so this one is 0, this one is 31. Start from here to here. Yeah, it's usually when we are showing things like when we are showing something like this is the MSB, this is the LSB, right? So that's the same. Why we have opcode and then funct, and you mean? So I mean, if you look at the table that we had, so actually, like, you see like something like store, right? So the immediate is here, and then for example, the other one, the RD is here. So regardless of how you assign them, there will be some instructions that are they all of them are like close to each other, and there will be some instructions that are all far from each other. So you can never really optimize. And then the other thing is that doesn't really matter that whether they are all at the same position or not. They are just wires, right? So you can just always connect this wire to here or connect that wire to here. It doesn't matter. From programming perspective, it would have been easier if they all combine and kind of box nice to each other. But in terms of hardware, it doesn't really matter. But when you're actually writing, so one part of your project would be like actually like decoding this. So at that point, you might feel like it's a little bit complicated. But as I said, for the hardware, it doesn't really matter. Any other questions? Yeah, so RD needs, so remember register has to be 5 bits, right? So you do 00001 if it's X1. Yeah. All right. So these are the 3 things to pay attention to. Another thing to pay attention to, you already talked about it. As you can see, some of the instruction, including these 4 and store and branch, requires both RS1 and RS2, whereas the immediate and load does not need RS2. On the other hand, most instruction actually have a destination register, but like store and branch does not need a destination register, right? So that's also another thing to pay attention to in this list of instructions. And then finally, the immediates. Some instructions, such as the R-type instruction, does not have any immediates, versus the ADA instruction and generally the I-type instruction has an immediate. For I-type instruction, the immediate is kind of nicely, packaged together. It's actually 12 bits, so the most you can show is 2 to the power of 12 minus 1. But example, something like store, you can see that the immediate is kind of scattered. So 5 bits is in RD and the rest is here. And then for the branch is even more weird because 3 bits plus the bit 11 is here and the rest is kind of here. So it's like a little bit weird the way it works. Why we spread out the immediates? The reason for the branch is actually I mean, you later on gonna see. So basically, it's the branch predictor gonna use this in order to predict. So as we gonna talk about the branch predictor, it's gonna like use some part of the immediate in order to make a decision and make a guess. And then they kind of realize that using the least significant bits and some of the high significant bits could be easier for the branch predictor. And that was one reason for doing that. Another reason is that, as I said, in order to keep some sort of structure, since you have very diverse set of instruction, each of which some of them needs RS1, some of them needs RS2, some of them needs RD, some of them needs immediate. You cannot really keep this structure. So for example, if branch equal wants to keep RS2 at this location, That's why they can, the only thing that they can do is that kind of like play with this immediate here and here. All right. And then another thing is that they wanted to like keep the 12 bits here, like the most significant bits on the top to, in order to show that like where the address is jumping and so on. So it's more of like the way that, you know, the decoding of the branch predictor works that we're going to talk about later. And the other thing is that, you know, no matter how you know, structure this, some of the instruction will look weird. Any other questions? Well, as I said, in terms of the actual decoding part, as long as you know where each bit is, the rest of it is just wiring, so it doesn't make any significant difference. All right, so the data path that we're gonna build, it's gonna look like this. Of course, it looks complicated, but we're gonna go through each of these different parts and then discuss why we're saying this. So the reason that I'm showing it here to have like a big picture of like how each different unit is connected to each other, but we're gonna talk about all of these things one by one. Okay. So let's start with the first part, the easy part. We already discussed this in the previous lecture. We said that everything begins with the PC. So PC is basically is this register, is this 32-bit register that kind of keep track of which instruction has to be fetched next, okay? So then this one is kind of connected to this instruction memory here, which it puts the address and gets the results out here. So this is basically our instruction, okay? This is our 32-bit instruction here. And then we said that here, depending on how many lines we have here, this could be either 32 bits or it could be lower than that. So basically, for example, it could be 20 bits and then the rest can be just ignored, okay? So that depends on like how big our instruction memory is. But for now, just imagine that this is also 32 bits, all right? Yeah, so the flow is from left to right. So if you go back here, the flow is from here to the right, okay? Yeah, so it's basically, this is the address. At this point, we have the instruction. At this point, we have the data. At this point, we have the calculation. At this point, we have the memory, and then we go back. So from now on, whatever I'm showing is from left to right. All right. So the next thing we need to do is, since for the next instruction, we need to create the next PC. For now, let's imagine that we always do PC plus 4. We always like, you know, run instructions one by one. So we need to create the PC plus 4, right? So what we do is that we create this, you know, extra wire here. We put it here. We add this additional adder here. And we add this PC with 4, the number 4, the immediate 4. And then we're going to put back this wire all the way back to the PC. And then just remember that this PC is basically a register. And if you remember, the registers, once the positive edge of the clock comes in, the D and the Q will be changed, okay? So this would be the Q basically. So this value here is, you can call it new PC or PC plus 4. And this value here is old PC. What happens is that once the new clock comes in, the value of new PC will be captured by the old PC. And now we're going to get the PC plus 4. Is that clear? So that's how we create the PC plus 4. And then this continues over and over again. And then you can see easily that at this point, we always have the new PC. And then, so at this point, with some delay, we always have the new instruction and so on. Now let's talk about the instruction, the register file. So at this point, we have the instruction. Now we need to read these values. We already talked about all these things. So register file has 2 read inputs, the read register 1 and read register 2. It's 5 bits because we have 32 registers. And then it has 2 output ports, which is RS1 and RS2. We also mentioned that in some cases, we don't need RS1, we don't need RS2. So we can easily ignore RS2 if we don't need it. We're gonna read it, but we're gonna ignore it. Any questions? Yes. The program So you always read the instructions, even in x86, you always read the instruction with the same pace. The only thing is that sometimes there are multiple instructions within that instruction. So there is a separate buffer for reading the instruction. So here it's not directly, this one is not directly connected. Sorry, here is not directly connected to the rest of the data path. Here is actually goes into this buffer that is the instruction buffer and reads those instructions. And then from there, you can actually read it from there. Does it make sense? So it's basically, let me actually, we're not gonna cover it in this course, but since you asked, so this is your instruction memory. And then in normal case, like RISC-V, you have your data path here, which basically is just from here, you read it and then goes directly through the data path. For x86, you will have in between have something like a buffer here that has this queue. So when you read instruction, you put it here, 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 and here. And the data paths basically consume whatever instruction that it needs. So the rate of which that you read instruction and you execute instruction may not necessarily be the same. You always have some instruction in the buffer that the data path can execute. Does it make sense? But again, don't worry about it in this course. We always have a fixed RISC 32 bits. So we always read directly from the instruction and put it into the data path. Yeah, so each time the clock goes to 1, you read a new instruction, and then so basically all these things happen in just one cycle. What's that? Oh, so the clock, I mean, like the queue changed. Like remember that we had register like this, that this was D and this was Q, and then this was clock. So whenever the clock comes in, the value of D will be stored in Q, right? So the Q will be updated by D when the positive edge of the clock comes in. Yeah, so when you're showing that, it means that it's updated by Q. All right, so register file will be like that. Any question from the register file? This read write? This one? The write data? The write data is actually a 32-bit data that we're gonna write to the register. But in order to write to the register, this value has to be equal to 1. So if it's not equal to 1, whatever you put here doesn't matter. Okay? Because we want to write a new value to the register, and register are 32 bits. So you need to have a 32-bit value that's been written to the registers, right? So for example, it's something like this. 1 RS1 equal to 1, let's say, right? So this is basically a 32-bit value because RS1 is a 32-bit value, right? So this line has to be 32 bits. Does it make sense? So all these lines are 32 bits, right? This one is 32 bits, this one is 32 bits, and this one has to be 32 bits. When we show the entire data path, we're actually going to show it that all of them, how many bits they are, and then you can ask again if it doesn't make sense, okay? Any other questions? The next step is the ALU. So ALU basically gets these two values and it actually does an operation for us. Remember when we talked about the ALU, basically it has two inputs, let's say X and Y. And what it does is that it calculates the function of X and Y. In the instructions that, in this sets that we're gonna have, we have add, we have sub, we have and we have or, right? So we have these 4 different, functionalities. So basically, this function could be one of these 4 different functionalities, okay? Any question here? So this ALU operation is actually a control signal that we're gonna talk about. And then this is actually gonna tell the ALU which of these 4 different operations it has to use, okay? And then another thing that we're gonna talk about is this 0 thing. So I'm gonna cover what this 0 is. And yeah, go ahead. Yes, the ALU you're gonna use for the immediates as well. So because the add I is nothing but adding two values. So in that case, this would be RS1 and this would be immediate. We're gonna actually talk about how we create that as well. For now, just think about this as getting two inputs, having a function based off the ALU operation, it decides which function to do. Yes, the controller will tell the ALU which operation to do. That's why you can, I mean, probably you're already familiar with the notation that I'm using here, but as you can see, this signal is blue. When the signal is blue in the data path that I'm showing, it means that it's coming from the controller. And then same as the red right here. Yeah. We're gonna actually talk about the exact value of the ALU operation, and then you can see how we actually tell the ALU which operation to do. For now, don't worry about the actual way that the controller going to generate the signals. For now, just know that, this is the way that is coming from the signal. So just think about all this abstraction way. So you just now think that this is the thing that coming from the controller. How the controller generated is something that we're going to discuss later, okay? And then the memory, as we said before, memory basically has address and write data. If it's a store, it's actually put a 32-bit value here. Otherwise, it gets the value here, which again is going to be 32 bits. But whether we're going to use all the 32 bits or not, depending on how big our memory is. But again, to make things easier, let's assume that it's 32 bits. And the value here is the read data. It's the value that's coming from the load word. So again, this one is 32 bits. And then we have two control signal, memwrite and memread that we're going to talk about later. Okay. Any questions so far? All right. So let's combine this a little bit and then talk about this a little bit more because we have an additional things like here and here and also here. So let's talk about these things here. So the first thing that you see here is this additional function called immediate generator. So why we need an immediate generator? So first of all, this part is coming from the instruction memory. So this is our 32-bit value instruction, okay? So you can see that it's divided into different pieces. One part is going to read read 1. The other part is going to read reg 2. The other part is going to write register and so on. And part of it is going to come to the immediate generator. If you go back into that table that we had, remember, for example, for load word, we had 0 to 11, like we have 12 bits of immediate, okay? What we're going to do is we want to add this to a value that is 32 bits, which is our RS1, okay? So before doing that, we need to sign extend this, okay? So this is basically do nothing but a sign extension, okay? And the reason we have an actual unit for it is because some of the immediates could be 12 bits, some of the immediates could be, more than 12 bits, could be 20 bits, and so on. So whatever happens is that it gets an input from here. It's going to sign extend it and create a 32-bit value here. So basically at this point, we're going to have a 32-bit value that is sign extended for the immediate. Does it make sense? No. It means that here the input of this unit could be either 12 bits, could be 32 bits, could be 10 bits, could be any of that. Just that's the notation I use. You can just ignore it if you're confused with it. Exactly. All the immediate generator does is sign extension, but since the length of the immediate could be variable, it's actually based off that it actually does the sign extension. We didn't show it in this, but if you go back to that table that we had, for some instructions, including the JALR, it was 20 bits. Yeah. It's not controlled by the controller, right? So it's just the value, it's just the wires that comes in and then create the 32 bits for us. Okay, so that's the immediate generator. All you need to know is that at this point we have the 32-bit sign extended immediate. So now we have this mux here. The reason that we have this mux here is because of some of the instructions needs to use RS2 for the ALU. Some of the instruction needs to use the immediate for the ALU, right? So for example, the add I instruction use RS1 and immediate versus the add instruction use RS1 and RS2, right? So in order to actually accommodate that, we add this multiplexer and we add this controller signal called ALU source, okay? And what it does is that if the controller sees that the instruction that's being executed is this add I, it's gonna change the controller value to 1, right? So in that case, this value gonna go here, okay? On the other hand, if the controller sees that uh, the instruction is an R-type instruction, is an add instruction, it's gonna assign 0 to here. So basically the mux is gonna select this value. So if you look at this point, we always get the correct inputs for the ALU. Does it make sense? Okay. So ALU source is again a control signal based off the operation. It's going to generate either 0 or 1. If you need the immediate, it's going to be 1. If you need the RS2, it's going to be 1. It's going to be 0. Can you repeat the question one more time? No, no, no. So this is actually all the 32 bits here. This is the wiring that we're gonna use in order to put the correct values to the immediate generator. Okay. We're gonna put all of them here, and then we're gonna generate all the immediates here basically. So the immediate's gonna generate based off what it gets. It's gonna generate the 32 bits that we want. Does it make sense? The ALU source is going to generate by the controller that we're gonna talk about. So again, the controller gonna decode the instruction and knows whether it's an add-I, it's an add, it's a subtract, it's a load, and all those things. And based off that, it's gonna make a decision that okay, which of these control signals, what is the value of each of these control signals? For example, if it's an add-I, it means that it needs this immediate value here. So ALU source has to be equal to 1. Does it make sense? Exactly. Exactly. Any questions? All right. So the next thing that we're gonna have is this additional, sorry about this mess here. So it's gonna be this multiplexer here, okay? So why do we need this multiplexer? So first of all, you see that the output of this multiplexer goes all the way to the right data of the register, okay? So why do we need that? So for R-type instructions such as add, we have RD, RS1, and RS2, okay? So what the value of the RD you wanna get? It's gonna get the output of this ALU, okay? So there's gonna be this signal here, okay? On the other hand, let me change the color here. Uh, on the other hand, if you have something like load word, load RD and some address, what we're gonna get is the address, the value of the memory has to go through the register file. All right. So this mem to reg is basically deciding whether the value that's going to be written to the destination register has to come from the memory or has to come from the ALU. Does it make sense? All right. And then you can see if it's coming from memory, the mem to reg has to be equal to 1. If it's coming from the ALU, mem to reg has to be equal to 0. Okay. And then another thing to pay attention to is that the data that's going to be written into the data memory is coming from RS2, right? So remember when we said that we had store word, we always written the value of RS2 to the address that is defined by RS1. Okay, so that's why we have this wire here that goes directly into the memory. The offset is for the address, okay? So the question is that if you do that, where the offset is being calculated. The offset is for the address, so that's why you see that this RS1, and then here it's going to be actually the immediate, and that's where it's going to actually connect it to the address. So the offset is going to be calculated like that. Any other questions? Okay. And then as we said before, this is actually coming from this multiplexer here as well. So going back here, so now we understand fully how why this part is working, right? Any question about this part? Yeah. So again, so here is the part that is coming from the instruction memory. So we have the 32-bit instruction here. It's going to be divided into different pieces, right? Depending on the table that we have. Remember, for example, bits 7 to 11 was the RD. So it's going to be basically this right register here. RS1 and RS2 had specific locations. So that's where these bits going to go for. Then at this point, we have RS1 and RS2, right? And at this point, we have our 32-bit immediate. Then we have this multiplexer here, which essentially what it does is telling that whether the ALU gonna get the immediate or is it gonna get the RS2. So for those instructions that are add-I or sub-I, etc., it's gonna get the immediate. For all the other instructions, it's gonna get the RS2. The RS1 always go directly into the ALU. So in ALU, based off the ALU operation, we're gonna do the calculations, could be add or multiply or subtract, etc. We're gonna talk about 0 in future. So for now, don't pay attention to it. Then we have the memory. So in some cases, if the memory is gonna be read, we're gonna use this in order to calculate RS1 plus the offset. So that would be the address of the memory. And then it's gonna be the value that's gonna be read from the memory. And then this multiplexer is used in order to show that whether we are using the value that is coming from the ALU directly, or whether this is the value that is used from the load word instruction. And this is going to be go directly to the write data of the register file. So we're going to write something to the RD, the destination register. Is that clear? Questions? So the immediate generator is going to sign extended based off the opcode. It's going to create the 32-bit for us. It's basically just sign extension. It's not going to create new data for us. It's going to just sign extended. Why do we do that? Because we need to, the hardware does not understand how to add a 10-bit value to a 32-bit value. The hardware only understands adding same length values. So it has to be sign extended somewhere. You could have sign extended here, but that makes some other confusion. So that's why you need the sign extension here. Yeah, yeah. So the inputs of ALU is always 32 bits. So before that, you need to do the sign extension in order to facilitate that. Yeah, if it's only, so this one is going to be 1 only if it's a load board, basically, right? It's going to be always 0, yes. If anything but the load is going to be 0. It's the labels from blue coming from the controller, yes. What happens to RS2? In which, where? So RS2 comes into this mux, depending on the ALU source. If the ALU source is equal to 0, RS2 gonna come to the ALU2. Does it make sense? Here? So this is the, yeah, this is the value of the RS2, yeah. I think you're confused with some of these things. So here the instruction comes in, and then we know exactly where RS1 and RS2 values are. We're gonna just pass it through here, okay? And then at that point here, we're gonna have RS2. On the top, we're gonna have RS1. Is that clear, or do you have? All right. So moving on. So we know that how this part works. So let's add a little bit more information to this. So now we need to handle the branch instruction as well. So before that, there's a question. This one here. So remember, store word gets the address, the mem address was equal to RS2. That was what the store does. So it gets the value of RS2 and store it. This is the value of RS2, right? That's why it's directly connected to write data. Yeah. But we don't write it unless this mem write is equal to 1. Is this what? No, you can see that's directly connected. The only thing that's controller by the controller is this mem write. So if mem write is equal to 0, we're not going to write anything to the memory. And then mem write is going to be equal to 1 only if it's a store word. The address is going to calculate it here, which is RS1 plus the offset, right? Yeah, like it looks like a puzzle, but you can figure it out if you look more to it, right? So now let's talk about the branch instruction. So remember the branch, what the branch needs to do is checking two things: the condition and where the PC gonna go next, right? If the branch is taken, the PC is not PC plus 4 anymore. It has to be PC plus some offset, right? So the branch logic is actually here. So this 0 signal is going to be showing that whether these two values are equal to each other or not. So we only have branch equal, right? So we're not going to do the branch less than or branch greater than and so on. So what does this do is basically comparing this value and this value. And if they are equal, this 0 going to be equal to 1, okay? If they're not equal, this 0 going to be equal to 0. So it's basically showing that whether the condition is true or not true. Okay, so this is what this 0 signal does. And then it's part of the ALU. It's basically just doing a simple subtract. Okay, so the ALU operation is basically subtract, and then it's going to create this 0 signal for us. If they're equal to each other, 0 going to be equal to 1. Another thing that we're gonna do is we need to add the PC with the offset, okay? So if you remember, the branch was doing PC plus offset and then jump to that address, okay? So that's what we do here. We have the PC here that is coming from the register here, and then we're gonna have our immediate here. I'm gonna talk about what this shift is, but for now, just think that this is actually just connected these two together. And this is nothing but an add. So basically we add the offset to the PC. Is that clear so far? Okay, and then the reason we are doing the shift is basically the way that the offset is created in RISC-V is that it always lets you to jump into even addresses, okay? So that's why you need to shift left by 1. So this is just a design choice that the designer made. So you never jump into into odd addresses. You always jump into the even addresses. And that's the reason, because you want to read 4 bytes together from the memory. And then if you had jumped to the odd addresses, that would have been much more difficult to read that. Okay. So this shift left is just for making sure that the value is not an odd value. You can do you can do 2 by 2, but I mean, the way, again, the way that the reader works is that it can read 2 bytes together. It cannot read 1 bytes by 1 byte by 1 byte in the instruction. So that's I mean, sometimes you actually wants to. So again, this is a choice that they made. So sometimes you actually wants to read 16-bit instructions. Again, we're not gonna cover it in this course, but sometimes you want to read 16 instructions, and that's why they actually add this into their system. 2, yes. No, no, it's not. It's adding this ability to being able to read 16 bits if you want to. But the way that the compiler and your code gonna generate this code is that basically the first 2 bits, it will be always 0, 0. So even if you shift 1 bit, it's gonna be the same. So for, again, it's not something to be worried about. It's just a design choice that they made in order to make sure that you're just only allowed to jump to specific instructions. The whole thing you need to know is that basically all this part does is PC plus the offset, but the offset itself is shifted to the left by 1 bit. What this ALU0 does is this one is RS1, this one is RS2. So if you remember, what the branch instruction was doing was this. So this was the branch instruction: BEQ, RS1, RS2, and some offset. Okay. So what it does say is that if RS1 is equal to RS2, then if this is true, then jump to PC plus offset. Okay. If it's false, PC should be PC plus 4. Does it make sense? So basically this line is just subtract RS1 from RS2. And then this 0 signal gonna be equal to 1 if these two are exactly equal. If not, it's gonna be 0. Adding and subtracting, it could be that it's actually doing the subtract. Sorry, doing the add, but generally they are the same, because and is also like you have to go through all of the bits, and also anding has to go through all of the bits. So it doesn't really, in terms of latency, doesn't really matter. But yeah, I mean, what the subtract is actually doing inside the ALU could be anding or even adding with the negative value. Both of them are, could be. So you basically negating and then adding. That could be also another way that you do the subtract. Other questions? All right. So so this would be basically our target address. This would be the branch condition. So at this point, we have the target address, we have the branch condition. So now we can jump to wherever we want. Yeah. So for this specific one, we just implement branch equal. If you had other things, you basically had to add it to your ALU operation, and then you have another different condition signal for all the greater and less than and all those things. For this specific one, we're gonna just focus on that 10 instructions that we listed. All right, so this would be the combined view. So the only thing that has been added is this mux here. So what does this mux do? So here, this is the target branch, right? So this is, here is PC plus offset, right? And here is PC plus 4, right? So at this point, we need to make a decision that whether we're gonna do PC plus 4 or whether we're gonna do PC plus offset. And then this PC source is nothing but this zero signal here plus some other control signal added together in order to create this signal, okay? So one is it a branch signal? And then is it the condition is equal to 0? Does it make sense? So we basically, in order to make a decision that we are jumping, there are two conditions that needs to be met. Number one is that these two values has to be equal to each other. That's a signal that is coming from 0. And then the second condition is that is actually a real branch, is not something else, because accidentally RS1 could be equal to RS2, but it's not a branch instruction. So that's why you're adding this together, and that would be your PC source. So if PC source is equal to 1, it means that we are getting this address for the next PC here. So it's basically this path going to be taken. Or if it's not a branch, or for some reason the condition is not true, then we're going to get the PC plus 4 to the next PC. Does it make sense? All right. So this is the whole data path. So as you can see, now you understand what each part is doing, right? So the entire thing is here. And again, we started from PC, right? The PC goes into the instruction. We're going to read the instruction here. We're going to divide the instruction into different pieces here. At this point, we're going to get RS1, RS1, RS2, and the immediate. And then we're going to use this marks in order to populate the correct data here. The RS1 going to come directly from here. The 0 signal going to be used for the branch instruction. The ALU results either going to go directly to the memory or going to be passed through this multiplexer here. And then this value is actually the value that the RD going to get, the destination register going to get. And then on top of that, we have all these control signals that in the next part of the lecture, going to talk about all these things. In addition to all of these things, we have this structure here for creating the next PC. So first of all, the PC goes here and going to be added by 4. So at this point, we're going to have PC plus 4. At this point, we're going to have the offset, which for some reason is left shifted. And then we're also going to get the PC here. So this is PC and this is the offset. So at this point, we have PC plus offset. And then at this point, we're going to decide whether we're going to jump to the PC plus offset or we're going to continue with PC plus 4. So this value that the register, this new value that the register going to get is going to be either PC plus 4 is going to be PC plus offset. Does it make sense? Anybody have any question? We're gonna show it how the 0 going to be connected to there. Once we talk about the controller, we're going to show that. This one? This one? That's the data memory. That's the entire data memory that's going to read data or write to it or read from it. SW and LWS, yes. As I said, in normal word, the instruction memory, this one and this one are the same thing. Since it would be much more difficult to show this together, we're gonna divide it like this. But in reality, they are actually the same structure. They're just different addresses, okay? They have separate port for the instruction, separate port for data. But again, to make things simpler, we just divide them into 2 pieces. All right, so don't forget the quiz next week. The format's gonna be 1 or 1 hour-ish, in person. It's gonna be in the same class. It's gonna be from lecture 1 to 5. So everything that we're gonna say today, all the way things that we started, nothing about next week. So next week, whatever I'm saying, it's not gonna be part of the lecture. And then homework 1 and 2. So 1 is already did. The homework 2 gonna be released today, and then we're gonna release the solutions before the homework on Tuesday. And it's gonna be a closed book. So everything that you need, we're gonna add it to the to the quiz itself. As for the quiz, we're not gonna give you physical papers. We're gonna just put it in the Google Docs. So Either bring a laptop or tablet, or you can even sit on your cell phone if you want to. So that's also totally fine. Just be prepared that we're not going to give you physical papers to just preserve, printing 500, 600 page of papers. Okay. And then we're going to have a sign-in sheet here that when you're leaving the class, just make sure that you are here and signing the signing sheet, so that because you technically can do it at home, doing the quiz at home. So I want you to make sure that you are actually here. And then for the grading policy, if you remember, we're gonna drop your lowest score quiz and your lowest score homework, but in the condition that you get more than 50%. So if it's lower than 50%, or if you decide not to take it, we're not gonna drop it unless you have actually a legitimate reason of not taking it. Any questions? Yeah, I usually thought Sunday, but thought that it's gonna be less, like, very short window, so I extended it to Tuesday. You mean the Sunday after? No, but if the homework is really, really long, we can always extend it. But I think it should be good. I mean, especially for this one, since it's gonna be part of the quiz, probably Tuesday night. Unless people are really, really busy, we might be able to extend it to Wednesday night. Somebody had a question there. I already answered your question. The quiz is here. Yeah, the location is here. You have to take a picture and then submit it to Gradescope, same way that you did for your homework. So you can totally fine if you use your own laptop or your tablet, as long as you don't chat with your friends and so on. But you can use your own device, and I'm trusting you that you don't do that. Question there? Something? Yeah. Doesn't have to be typed. You can bring a piece of paper, write it, take a picture, and upload it. That's also fine. What's that? It can be typed. It can be typed. Yeah. Yeah. In theory, typing should be enough. Yes. You don't need to draw figures for the quiz. Yes. It's just basically it's going to be 3 questions. One is like something like an assembly code that you need to parse what the code is trying to do. The other one is something about microarchitecture, trying to like calculate some values and things like that. And the last question is like short true and false question that, there are some statements you have to say whether it's true or not. Or basically would be covering most of the things that we discussed in the first 2 lectures. You have to submit it before leaving the class. Yeah. So it should be like 1 to 1 hour ish, and then you can have like 10 or 15 minutes to submit it. We will put the tables in the file that we are giving you, so you can actually like scroll down and see all the files. That's why I don't want to print all those things, because 150 of you, 5 pages each, it's going to be a huge number of papers that I'm going to print, which I don't want to. I mean the quiz. I mean, again, some intermediate values that's like, how you, I mean, don't do the final value, just show that's like how you ended up like finding this value. It doesn't have to be anything specific. Maybe just showing that, here the intermediate value that you thought is correct. So actually, I mean, the quiz is going to be like 2 inner functions together, and then kind of like you have to first figure out what the first function is doing and then what the other function is going to do. So it would be easier to say that, okay, I think this function is doing this because of these reasons. And now based off that fact, I'm using that value in order to compute the second function. So that's going to be like that. So it's going to be easy to describe how you actually end up with that value. No, we're not going to have lectures. All right. So what time is it? Let's have it like 2 minutes, 3 minutes. We're back at 5:10. Yeah. Closed book, closed notes. Yes. Yeah. Yeah. Yes. Uh, I mean, RISC-V is not a microarchitecture in general, so yeah, it's an implementation of RISC-V, so it's not something that, any implementation is a RISC-V implementation as far as you can support those instructions. So that's why, for example, we have that shift left in order to satisfy the requirements that they put in the ISA itself. Mm-hmm. 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 It has, but you don't have any control over not clocking the rest of the uh so there are ways of, for example, so first of all, reading things is actually where, like, flipping bits is actually where it consumes the energy. So if, for example, there's no bit flips inside the ALU, it doesn't really consume that much energy. On the other hand, most of these parts gonna be used anyway. The only part that may not be used is the memory, right? Because most of the instructions are not actually dealing with the memory except the load word and store word. And then unless you don't put anything onto, so unless this memory read is not equal to 1, you don't necessarily go into the memory. So that's where you save the bulk of energy, basically, right? But the rest of it is gonna be used anyway, right? You always need to read the register file anyway. You always need to use the immediate generator anyway, and these things, right? You mean this one or this one? Uh-huh. Yeah, yeah. Yeah, yeah, yeah. Yeah, yeah. Yeah, there is nothing you can do about that. So you cannot not calculate PC plus offset because you're not gonna use it. Because if you're gonna use it, you don't know when it's gonna be. And then since everything is happening simultaneously, you cannot say, okay, I'm gonna wait until knowing whether I'm gonna use it or not. Because then you're paying the delay, right? You can say that, okay, I'm not gonna compute the PC plus offset unless I know it's a branch. But on the other hand, you're paying the penalty of not having that value if it's a branch, right? So you're willing to pay that energy penalty in order to have a performance, because performance is always the most important thing, right? Mm-hmm. So there was someone else that had the same problem, and then we said that we can drop that last quiz for you. So, but in that case, we won't drop the other score. So we can try that if you want to. That's fine. Send me a DM, and then I'll give you the permission for that. The week after Thanksgiving, in December 2nd or something. Uh-huh. Basically, the read enable would be this read write. Right, sorry, the write enable would be this read write, right? So if the read write is 0, it's same as the enable. And then read enable is basically this mem read, because if mem read is equal to 0, then read enable is 0. And the same write enable is again this mem write, right?
overarching summary, what you've done in this data path by combining all these like sub pieces together is like for the 10 like instructions that you wanted to implement in the CPU that you said, you just basically went on implementing them one at a time and then you combine them together.
Exactly.
Okay, right. So would the question like on a quiz actually ask us to design a CPU like this, or
No, no, no. The
okay,
project is implementing this basically.
okay, all right.
But not for you guys. So you're gonna implement this in our order, but yeah, everybody else gonna implement this in Verilog. Uh, we're gonna now in quiz now we not so it's gonna be very difficult to actually parse this, but in homework actually one of the question is adding an additional instruction. So what you need to do is, let's say I'm telling you that I need this instruction added to this list of 10 instructions. Now you have to figure out what are the changes you need to make in this existing data path in order to be able to support that. So that's the question that you're going to see in your homework this week.
Okay, all right.
Yeah.
For the quiz, when you say it's closed book, is that also closed note?
Yeah, it's closed book and closed now. Yeah.
So basically, like, there's gonna be no deploying. For the microarchitecture question, what do you mean? Like, I get the assembly question, basically like one of the ones on the homework. But for microarchitecture, what do you mean? Like something like this?
No, you have to calculate some timings and things like that. So, uh, what's that?
Did we go over timing and all that stuff? Or are we supposed to remember that for the
Uh, no, it's like, knowing. I'm not gonna go through the details, but like you have to like. I mean, we're actually gonna talk about it a little bit later in this lecture actually.
Oh, okay. I
Yeah.
like because I don't remember you talking about it before, so I was like,
Yeah.
okay.
All right, guys, let's start. It's 5:15.
What's the difference between this and out of order?
Oh, we're gonna talk about it.
Oh,
Don't
okay.
worry. All right, guys. So let's continue. So now let's talk about all these control signals. So far we said that these are the signals that's gonna come from the controller. Now let's actually talk about the exact details. Okay. So these are the list of the control signals that we're gonna use, right? So the read write is the one that decides, whether we are writing to the register or not. The ALU source was the one that picking between the immediate and RS2. The ALU op was the one that deciding which functionality in ALU we want to use. Memory and memRight was those two control signals for the memory. If it's a load word or if it's a store word, we need to assign this to one. And then mem2reg was that last multiplexer on the right that decided whether the data is coming from load word or whether the data is coming from the ALU. And finally, the PC source was the one that deciding between PC plus 4 and PC plus offset, right? So these are all the control signals that we're going to specifically need for this data path. If we wanted to, added additional instructions or having different, data paths, we would have had, different control signals as well. Okay. So the state machine that we're gonna make things, keep things simple and say, okay, we're gonna have 3 different states for every different instruction. So we have different instructions, we have 10 different instructions, each of which gonna have 3 different states. The fetch and decode stage, which we're gonna call it FD, the execute stage, we're gonna execute, and the write back stage, which we're gonna call it WB, okay? And then again, to just remind you that the instruction that we had, here are the list of the 10 instructions that we have. So again, pay attention to the locations, to the opcodes, func tree, and all those things, okay? Uh, so in order to create the states and design the FSM, so basically the first thing that you need to do is always assign everything to 0. So all these signals that we have, let me all these control signals 1 2 3 4 5 6 7 signals that you have has to be first initialized to 0. Okay, and this is called active high kind of design. By active high I mean if it's equal to 1 they're active, if they're equal to 0 they're not active. You could have a different scenario as well. Initialize everything to 1, and then if they are active, you assign 0 to them. So that's called active low. Okay, so that's the difference between active high and active low. We're gonna pick active high in this class. Okay, so basically what we're gonna do is that for each instruction we start from all 0 signals, And then depending on what the instruction at this stage, we're gonna assign some values. So for example, if it needs the immediate, we need to change the ALU source, etc., etc. Does it make sense? All right. So the first step, obviously, as you remember, we said that everything starts from this initial state, okay? This initial stage is usually called decoding. So we need to decode the instruction, understand what this instruction is, right? And then what we usually do is we use the opcode first, and then we're gonna use the opcode to understand what type of, what type of instruction this is. Is it an R type? Is it an I type? Is it a store? Is it a load? Or is it a branch? Then if it's actually, for example, is an R type instruction, then we need to go deeper and then check the func3 and func7. So C-wise, if you want to think about this at the high level language, it's basically a giant switch case, right? We're gonna use a switch case saying that, okay, switch based off the opcode. If it's 000, for example, it's an R type, then you have another switch within that switch saying that if func3 is equal to this, uh, check these things, and then again on func7. So basically you have this back to back to back switches within each other in order to actually understanding what this instruction is. Does it make sense? Actually, in your project, you're gonna implement this, so you're gonna learn more about how exactly to do that. But again, as I said, conceptually, it's basically a big switch case. Have a question? No. All right. So now combining the data path and controller together, this is how the signal would look like. This is how the data path would look like. So as you can see, the controller is sitting here. What the controller gets is basically this, 7 bits, the opcode value here. We're gonna talk about what the func also gets, but for now, just the opcode would be enough for the controller to assign the values. As you can see here, we actually put the actual values of the instructions here as well. So for example, bit 15 to bit 19 would be the RS1, bit 20 to bit 24 would be RS2, etc., etc. Another thing that you can see here is that we actually create 0 ANDed with branch instruction and then added here. So we have this additional control signal called branch. And what this does is basically just checking the opcode, knowing that whether this is equal to branch equal or not. If it's equal to branch equal, we're gonna assign this value 1 to this, all right? And then you can see that, for example, read write is going here, ALU source is going here, the ALU up is going to this thing called ALU control, which in next few slides, I'm gonna talk about this part here. And the rest is you already know. Any question here? What's that? It's an AND gate. So it's AND branch with 0, and that would be the selector for this multiplexer. No, this 0 is this 0 signal. It's called 0. It could be 0 or 1. Yeah, it's a flag, basically. You mean this one? So no, the func3 and func7 gonna be used here. I'm gonna talk about exactly how we create the difference between add and subtract and or actually. Yeah, the reason that they have the same opcode for a reason that we're gonna discuss in the next few slides actually. From where? It's here, right? You see it? It's going here. Maybe, can you see it now? Okay. I cannot hear any. Can you speak a little bit louder? Sorry. Yeah, so So essentially the way it works for now is that, and we're actually gonna let me talk about the next slide, and then you will understand how this works. We're gonna talk about the ALU controller. Just wait. All right. So now we want to know how to assign this value as you asked, right? So there are two approaches, which in this lecture, we're going to talk about the first approach. And that is just assign all the control signal in one cycle. So basically what it does is that we read the instruction, and then we say that, okay, this is a load. Then we're going to say, okay, what is the path for the load? We're going to assign all the control signals for the load all at once. All right. And then for the next cycle, we're going to see, for example, add or add-I or whatever instruction that we have. We're going to assign all the control signals all at the same time. What do I mean by that? So basically, I know, for example, add gonna use RS1 and RS2, right? So I'm gonna just say that, okay, this, for example, multiplexer has to be equal to 0 because we want to use RS1. Another thing that we know for add is that we're not gonna use memory. So we're gonna assign 0 here, we're gonna assign 0 here. Another thing that we know is that this one has to be come from the output of the ALU. So this one has to be also equal to 0. This branch signal has to be equal to 0, and all those things. So basically, you can have a table saying that, okay, these are all the signals that for this specific instruction, here's the, all these values that each of these, control signal has to have. And then you repeat that and create this table for all of them, okay? So this is very simple, and it's called single cycle processor, okay? So every instruction executed in one cycle. And then we done with the instruction, goes to the next cycle, read the new instruction, execute it, and go to the next one and next one. So this is a single cycle processor design. All right. Any questions? All right. So the table that we're gonna have are gonna be looks something like this. So we have our R type instruction, we have I type instruction, load, store, and branch. And here are the opcodes of all these things. And I'm actually listing all the control signals for all of them. All right. So what we're gonna do is that we're gonna actually populate the numbers for all of these. Okay. For example, the read write for these three instructions would be equal to 1. For store and branch equal, the read write should be equal to 0 because essentially there is no destination register. The ALU source for the R type is 0. Since I and LW and SW need an immediate, it has to be equal to 1. For the branch again, it has to be equal to 0 because we are comparing RS1 and RS2. You can actually follow all these other signals as well. For example, for the branch, everything is equal to 0 except obviously the branch. For mem read, only the load has to be equal to 1. For mem write, store has to be equal to 1. And from mem to read, only load has to be equal to 1. And then we're going to talk about what ALU op should be. All right, so everything except ALU op should be clear. Any question? All right. So now let's talk about the ALU operation. All right. So we're gonna have this table here, and then we're gonna create this ALU operation based off the functions. All right. The functions that we're gonna get is that for the load and store, we need add. Why we need add? Because we need to calculate the RS1 plus the offset. So LW and SW has to get the add. The branch equal is, as we said before, is going to subtract RS1 from RS2. So branch equal needs the subtract operation. And then we had all these R type and R type instructions. So some of them needs add, some of them needs subtract, some of them needs and, some of them needs or. All right. So the way that we're going to assign this value, we're going to say that 0, 0, 1, 0 are going to be add. So as you can see, all of these are 0, 0, 1, 0. The subtract going to be 0, 1, 1, 0. And then the add going to be 0, 0, and then the or going to be 0, 0, 1. All right. So we're going to cover everything from all of them. Does it make sense? So basically, ALU op is any of these four different instructions, this four different bits. We can create the correct functionality that is needed for that instruction. Any questions? Oh, we're gonna get through that. We're gonna talk about that. Any other question? All right. All right. So another thing that we're gonna do is that uh, since we have func3 and func7, the trick that we're gonna use is that based off the func3 and func7, we're gonna change this ALU control inputs. Okay. So again, this is the table that's based off the where am I? Okay, here. So so this is the 2-bit value that is coming from the ALU up. Okay. And then for load store, we're gonna use 0, 0. For the branch, we're gonna use 0, 1. And then for the all these R type instructions, we're gonna use 1, 0. And then for the func3, we're gonna use this ALU control values. Basically, the way this works is that in order to make things simpler, so for the controller, so that the controller doesn't look at the func3 and func7 at the same time, and then because we could have easily just look at the opcode and then populate func3 and func7 here, we use this trick basically in order to use just these 2 bits for the ALU control, and the ALU control gonna generate this ALU operation for us. If you look at this, it's basically similar to this here, and then it's exactly the same functionality that we want to have for every single operation that we want to have in our 10 list of 10 instructions. And then on the other hand, as you can see, is that basically the ALU control, based off these values that's coming from here, and then based off the func3 and func7, gonna generate this 4-bit values. Is that clear, or do you want more explanations? So this is the way it works, right? So the controller gonna just generate these 2-bit values, and this is the table that the controller gonna use. The ALU controller gonna get these values, and then gonna add it with this func3 and func7, and based off that, it's gonna create this ALU control inputs. All right. So this way, we are just looking at the opcode here. We only created 2 bits here, and then we also get the func3 and func7 here, and based off that, we are creating this 4-bit here. Because for the ALU op, in order to, so think about the FSM machine as state by state machine, okay? So we need to decode in one cycle, right? So we need to to understand what instruction this is. And in one cycle, the only thing that we can understand is the opcode. We can read just the opcode. If, for example, if it's add and subtract, we need to jump to another state and say, okay, is this an add or is this an subtract? And then we need to jump another state in order to read the func7. So basically for add and subtract, we need to jump 3 steps, versus for load and store, we know already that which of these instructions is there, right? So the decoding part for add and subtract is 3 steps. For the rest of the instructions is only 1 step. Okay, so this is not something that we want in the controller, because then it means that the add and subtract would be much more slower than the rest of the instructions. So the trick that they use is that saying that, okay, the opcode for all of them is the same. So you know already that this is an R-type instruction. And with this 2-level tricks that they are using, now they can actually assign the correct functionality for the data. You're not getting at the next cycle. You get it at the exact same cycle, right? So here, remember, this is the instruction 60, right? The controller gonna, at this point, at the same cycle, gonna know whether it's an R type or an I type. At the same time, the value gonna go here, and then the func3 and func7 gonna go here as well. And then it's gonna know which value is gonna populate for this. So for both, for example, load instruction and the R type instruction, the delay is exactly the same, right? Exactly. More work for the load instruction, but same amount of work for everybody. So you just add them together. if you look at the, so yeah, you just so I don't put the logic here, but the way it works is that you just add these bits. This, I think these are the lowest significant bits, and the highest significant bits would be the add of these three bits together. Let me see if the logic is correct. 1 second. I think you just, yeah, I didn't put it here, but the trick is this. You have this ALU up, which is this 2 bits, and then you have this funct. If you add or them together, you actually end up with this value, and that's why you get the 4 bits. I didn't put it here, and then I don't actually remember how exactly we did it, but if you play with it, you will figure it out. You see the trick? Yeah, sorry, I forgot to put it here, but generally this is the trick. You just add these two values, you concat these 2-bit values with the rest, and then that's how you end up with this 4 bits value. I should have put it here, but I forgot. Can you say the last word? Yeah. So yeah. So again, the why part is we want to be able to have the exact same processing time for all the instructions. Okay. One trick that we could have done easily was that for all the R type instructions, we could have separate opcodes, and that would have been easy enough, right? There were two downsides for that. One was the switch case that we had, the decoder that we had would have been much more complicated because now we have more states. We have every different steps for add versus subtract versus and versus or. And since the majority of the instructions are actually R type instruction, it would have been very, very more efficient if we have just one opcode for all the R type instructions. Okay. So that's the number one reason that we have the same opcode for all of them. Could have had one opcode for all of them. Now that we have the same opcode for different R type instructions, we want to avoid this scenario where in order to understand which R type instruction this is, the controller has to take multiple steps. Okay. For example, in the controller, we could easily go through func3 and func7 until figure out which instruction this is. But the problem with that is that it takes more time for some of the instruction. It takes less time for the other instruction. And that's what we don't want. So that's why we create this trick that we have this 2-step kind of decoding stage where essentially we have this table that's saying that, okay, these are the values for the ALU up that is going to generate it with the controller. And then what we're going to do is that we're going to concatenate that with the func and func7, which has a logic that right now I don't remember, that it's going to generate this value automatically for us. And then once we have that, based off this table that we showed here, basically we have all the functionality that we want, right? So it's kind of like, take a step back. First, we know that we need these operations here, and then we create these two tables correspondingly in order to create that operation for us. Is that clear? The X's means we don't care. Basically, it means that whether it's 0 or 1, we don't care. When we say X, it means that. You don't add them, you concatenate them. Yeah. I believe I don't want to spend too much time, but I think, yeah, I have to actually look at it. It's hard to figure out by just looking at them, but it's basically some sort of weird concatenation of these 2 bits with ANDing with this bits that creates that 4 bits. But it's a pattern. I'll post it on the campus fire and we'll see how it works. Yeah, we only thing that we care about at the end is this control signal that's going here, right? And then if it's follow this pattern, we are happy. And then the way that we create that is with this trick. Does it make sense? Yeah, I think if I had added that logic, it would have been much more easier. Sorry about that, but I'll post it and then it will be much more clear. Yes. Any other questions? All right. And then I already described how this works, right? So we are basically adding this extra AND gate here that AND the 0 bits with this branch bit. And that would be the selector of this multiplexer. So now let's see what is the path for each of these different instructions, okay? So if you can see, some of them are a little bit, uh, fainter. Some of them are brighter than the others. So for example, for the R type, we start from here, we get the PC, we read the instruction, we go here, we divide the instructions. The first 6 bits gonna go here. The next 4 bits gonna go here. The rest gonna go here, here, and here, okay? Since it's the R-type instruction, we don't need the immediate generator, so you can see it's like a slightly, in lower color basically. But this part is actually going to be used for the ALU control, so this one is correct. Then here, what's going to happen is that we're not going to select this one. We're going to select this one. We're going to go here. We're going to go here. We're not going to use the memory. We're going to use this here. We're going to select it from here. I'm going to go back here, write it to this register. On the PC side, we're going to go here. PC plus 4, going to go here. This part is not going to be active. So we're going to select this here. We're going to go back here. Is that clear? This is the, the life cycle of an R-type instructions. For a load board, again, we're going to start from the PC, going to go through the instruction, going to, again, divide the instructions. This time, we're going to use the immediate generator because we need the offset. We're not going to read register 2. We only need RS1. So this value here can be ignored. We're going to populate it from here. We're going to go directly here. So this value is not going to be used. We're going to actually read it from the register, from the memory. We're going to go here. We're going to select this one. So this is actually coming from here. We're going to go all the way back. Again, we need to write it to the data. On the PC side, it's the exact same path as the R type. So it's basically here. Any question here? And then you can actually draw the same picture for the store, from the immediates, and so on. All right. So one thing to note is basically all of these things happen simultaneously. Okay. So it's not like, so think about this as you have a water here, and the water starts going into all these directions at the same time, which means that, for example, the delay for getting to this point is the delay of here plus here plus here, okay? It's not gonna wait until the value gets here. The delay is gonna be this plus this plus this, right? So if I'm asking you what is the delay for this value to be calculated, you're going to say it's going to be the delay of the reading the PC plus the delay of adding plus the delay of multiplexer. All right, so that's the delay of this value become a valid value. Another question might be, okay, what is the delay at this point? The delay at this point is the delay of PC plus the delay that it takes for reading the instructions in SMEM plus the delay of reading the registers, read, plus the delay of this ALU. So now we reach at this point, right? But you might ask that there could be a different path for reaching to this point as well, because this is an immediate value as well. So then you have, so let's say that what this path is, how much this path is taking time. It's going to be, again, PC plus insmem plus immediate generator. So this time we don't have the delay of register file, plus the multiplexer here, plus the ALU. So if I'm asking you what is the delay at this point, you have to calculate this delay, and whichever is the maximum would be the delay at that point. Does it make sense? Because these are the two separate values that at the same time goes together. You have to compute the path for both of them. And then at that point, whichever comes later, that would be the bottleneck. That would be the delay at that point. All right? Does it make sense? Any questions? Read and it can read and write. So read and write are completely separate. They can happen at the same time. But keep an eye that this value actually coming from this point. So actually reaching to that point is much more slower than reaching to this point, right? So the value that is valid for the register write comes much more later than the value that is valid for the register read. Same register on the same cycle, exactly. Of course. Either you just do the parameter saying that, okay, same as I'm writing it here, or you just actually have the values. Okay. So we almost reaching the end. So single cycle, very simple, very easy to understand, very straightforward, but it's unfortunately not the most efficient. Why is not the most efficient? Because essentially we are paying the price of the longest delay. Why we are paying the price for the longest delay? Because essentially we want to do everything in one cycle. And then we have, for example, different path for the add instruction versus a path for the memory instruction. But we want to use the same clock cycle for both of them. So what we need to do is that saying that the clock cycle has to be the maximum of all these delays, and that would be our clock cycle. Whereas for example, the add instruction could have been much more faster than the memory instruction because it's basically going through a much more different path, right? So basically the critical path in this design that we have is actually the load instruction. And if you look at the load instruction, you're going to see that it's actually PC plus instruction memory, register file, ALU, data memory, register file. So that's the delay that we're actually going to see. But for the add, you're gonna see that this part is not gonna be used. So we're gonna actually go through this path. So we are adding the extra delay of the memory, which is actually, in fact, is really huge delay to all these instructions. And then that's how we decide how long the clock cycle should be. And that would be very inefficient, right? So we basically saying that the clock should be max of all paths, right? And then that happens to be the max of memory, basically. So the clock is that the delay of the memory. And unfortunately, this is really slow because if you remember, we said that we always doing the common case, making the common case faster, and memory is not the common case, and we don't need to actually pay the price of the memory for all the other instructions. Okay. So what should we do in order to kind of get rid of this? There are multiple solutions. For example, you can have a variable clock saying that, okay, for the add instructions, I'm going to clock the system faster. For the memory instruction, I'm going to clock the system slower. Or another thing that I can do is that, for example, for memory, I'm going to spend 3 cycles. For the add instruction, I'm going to spend 1 cycle. But all of these things means that, the circuit that we're going to get is going to be much more complicated because essentially, first of all, variable clock is not an option because designing a clock is very challenging in this complex systems. And then multi-cycle design means that you have to have a very complex controller that has to understand that for some instructions, it has to create multi-cycle, control signals. For some instruction, it has to create one cycle control signal. But again, that would be very complex controller system. Yes. So the load word instruction basically, because load word going to be on the critical path, because we want to write save the value of the load word into the register file, right? So we cannot go to the next instruction before writing this. So that's why we need to wait for all this time that the data loaded and coming here, then gonna go flow and then go here, right? So that's why it's like a huge delay that we have to wait. And memory, as we're gonna talk about, hundred times or more slower than the actual processor. So we're actually paying a huge penalty here. I mean, if you have to do the memory multiple times anyway, there's no way to go around it. So that's what we are saying is that since majority of the instructions, only probably 20% or so is memory instructions, you're kind of like, wasting another 80% of your time on the memory instructions, because you could have had much more faster time for all those 80%, and you could have paid the penalty for only the 20%. But with a single cycle, you are paying the penalty for the entire 100%. Does it make sense? All right. So what we can do is what is called pipelining. Okay. So the pipelining is basically saying that we can break the system, we can break the processor into multiple stages, and then it's essentially each stage could be one cycle, and then everything can move on to the next stage after one cycle. Okay. So this way we can break the critical path. So for example, the pipeline stage that we're going to use in this course, and I'm going to extensively talk about in the next lecture, gonna look like something like this. So we're gonna actually put registers here, and then we're gonna say that, okay, this part takes one cycle, 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 and this part's gonna take one cycle. And this way we are actually breaking the path, and then we are managed to, run the clock much more faster. How? We're gonna talk about it in the next lecture, okay? So basically we're gonna use this notion of state, combinational logic state, in order to save the results. And this would be this idea. This is the combinational logic, this is state, this is state. This is the combinational logic, this is state, this is state, and so on. So we're gonna flow the data from left to right using this registers. All right. So we're gonna talk about this and how it's actually helping us into improving the performance using this iron law. Yeah, give me a second, okay?